Welcome back, students. Let us finally go to the last segment of this video lesson, Section 3, Subsection 3.2, Local Extrema. These kind of problems can be really bad. What you need to do in general is to take the derivative, set it equal to 0, find out all the x-coordinates of the critical points, and then determine their nature one at a time. It can be a great challenge, but, well, we are living in 21st century, so I'll allow you to cut the corner by using technology. So before trying any of those methods, I strongly encourage you to take the derivative, I strongly encourage you to plot it. Before taking the derivative and doing all this computation, plot it first. You're going to have an educated guess of what's to come, and that'll make your problem solving much easier. Here's a graph. What do you see? We have local maximum here, local minimum here. All you need to do is to identify exactly what these x-coordinates are. This one looks like -1. This one, just by looking at it, is a little bit unclear. So what do? Take the derivative and then set it equal to 0. So what is this? 3x minus 1, x plus 1. Is that right? Yeah, that's right. So x equals a -1 or x equals 1/3. So this local minimum corresponds to x equals 1/3. That local maximum corresponds to x equals a -1. That's all you have to write down because you have the graph. -1, excuse me. Okay, here we go. Local minimum at x equal to -1 and the local maximum at x equal to 3. That's all there is. Of course, if you don't have the graph with you, then you have to justify, and that's gonna be an ordeal. I'm not gonna bother. How about the next problem? Again, I encourage you to start from the plot. So we have this kind of plot. Looks like we have a local minimum here, neither maximum nor minimum over here. But if you just look at the graph in naked eye, whether this is actually -1 or not is going to be hard to see. This one will be pretty straightforward. This one is going to be harder to see. So what you need to do is to do some computation, but this graph allows you to bypass the justification or testing the nature, to be a little bit more precise. So take the derivative. What is it? 12x to the 3rd power, isn't it? Minus 24x equal to 0. Is that right? No, squared. So 12x can come out. We have x squared minus 2x plus 1, which is 12x, x minus 1 total quantity squared. Setting it equal to 0, you're going to get x equal to 0. As you saw, this was local minimum, and x equals to 1. You saw neither maximum nor minimum. That's down here. Now, how about concavity? Oh, okay. It's not impossible in this particular case, so let's consider concavity, intervals of concavity. It looks like concave up to here, concave down, and then concave up here. How do you get those? If you take the second derivatives, you'll know. Second derivative is positive here, concave up, and second derivative is negative there, positive again. So let's find out the second derivative. Oops. Second derivative. Start from here and take the derivative again. So what do you get? 36x squared minus 48x plus 12 and set it equal to 0. What do you get? You get 12 out, 3x squared minus 4x plus 1 equal to 0. 12. So this one is 12x, 3x, and x minus 1. Let's see, is that right? 3, okay. Negative 1, okay. Negative 1, negative 3, that's alright. We get x equals to 1, and these are inflection points. X equals to 1 right here, x equal to 1/3 may be somewhere here. That's where the concavity changes. Concave up, and then here inflection point, concave down, and here concave up again. These are the x-coordinate of the inflection point. So what conclusion can we draw? Let's see. We got local maximum, local minimum neither, inflection point. Okay, let's go to the conclusion. Decreasing in the interval negative infinity to 0 in the interval 0 to infinity, isn't it? This is neither maximum nor minimum, so increasing just goes on all the way toward. Alright, concavity, we have to use these. Negative infinity to 1/3. One-third to 1. Concave up again in 1/3 to infinity. Well, let me minimize all this. Okay, I think you can see everything in the same viewing window. Oh, never mind, let's erase them all. Okay, that's better. All the computation and conclusion put together. Take the derivative set it equal to 0 to find out critical numbers. Second derivative set it equal to 0, x-coordinate of inflection points. Now all those numbers are there, so look at the graph and then type in the conclusion. Decreasing from negative infinity to 0, increasing from 0 to 1, and then all the way to infinity. Concave up in negative infinity to 1/3. Up to here. Now concave down from 1/3 to 1. The second inflection point, x equals to 1. From here to infinity, concave up. How about some other problems here? Some of those problems are, well, what can I say, really, really long. and especially the concavity computation may be either impossible or too difficult to do. I wouldn't bother. Let's consider just one problem. How about something like this? This looks challenging enough. Okay, we have to use product rule and chain rule in order to calculate the derivative. Well, here is the graph. Decreasing local minimum, increasing local maximum, decreasing, and then we have horizontal tangent. Horizontal asymptote, excuse me. How about concavity? Concave down up to here, around here, concave up, concave down up to here, and then concave up. So we expect 3 inflection points. X equals to, I don't know, about negative 1 point something, positive 1 point something by symmetry, and then x equal to 0, again by symmetry. But then again, am I really looking for the inflection points? Well, let's do as much as we can. Take the derivative. Derivative of first function times second function plus first function times derivative the second function. You have to set it equal to 0. This is a derivative of the second function. Please note that I used the chain rule. So set it equal to 0, you'll have to factor something out, and the exponential can be taken out. So let's do that. Take this exponential out, and then what's left is 1 minus 2x squared. Set it equal to 0, what do you get? We get 1 is equal to 2x squared. This factor is equal to 0. Or let me write like this. Equal to 0. 2x squared is equal to 1. Squared is equal to 1/2. So what do you get? X is either plus or minus square root of 1/2. Somehow I don't like this font. Okay, let's write like this. Plus or minus square root of 1/2. And if you want to calculate this thing, you can calculate square root of 1/2, and then let's mathematically calculate it. 0.07 something. So here we go. That's approximately equal to plus or minus of, where's plus or minus? That 0.7 something. Okay, where are they? Right here and right there. So what can you conclude about increasing, decreasing? Decreasing in the interval negative infinity to negative square root of 1/2. Negative square root of 1/2 to positive square, oops. Okay, positive square root of 1/2 and then decreasing in square root of 1/2 to infinity. There goes the conclusion. Decreasing, increasing, decreasing. Now, do we have time for second derivative and concavity? Too tedious. So I'll just ask Mathematica to do the computation. Oh, I didn't even ask Mathematica to do that computation, so I guess that's something I did even gave up. So I'm not going to worry about concavity here. Looks like concave down up to somewhere around here, concave up to 0, concave down up to about 1 point something, and concave up again. But in order to find out all those points, we have to take the second derivative and set it equal to 0 and solve that algebraic equation. Looks like too complicated. Even critical points, those are hard enough, so let's stop here. And the other problems are kind of like these.